Imagine for a moment an autonomous delivery drone. Its whole purpose is just delivering packages. Simple enough.
Right. Seems straightforward.
But its reward system is incredibly basic. It only gets, a thumbs up, positive reinforcement when a package actually arrives safe and sound.
Okay, so only reward on success.
Right. And then one day, mid-flight, this drone just veers off course and smashes right into a big oak tree. Total failure. Comes out of nowhere.
Ouch. Not good for the drone or the package.
Definitely not. And the question is why? Well, it's because its entire learning, everything it knew, was based purely on that single sparse reward package delivered.
Yeah.
It never explicitly learned about obstacles. Nothing in its programming said trees are bad, avoid them. It just didn't have that negative feedback for hitting things.
So it learned the goal, but not the constraints, not the how.
Exactly. And this isn't just some hypothetical tech glitch. It's actually a really stark illustration of the limits of learning purely from outcomes, what we call a model-free strategy. So let's unpack this a bit. This cautionary tale, this robot learning the hard way, it's not just about the nitty-gritty of AI programming. It's actually a perfect lens, I think, for understanding how we as humans navigate our own incredibly complex world. So today, we're diving deep into this fascinating field called computational rationality.
That's right. And our core mission, really, in this deep dive is to explore the fundamental mechanisms, the ways both human minds and AI agents make decisions.
How we choose what to do.
Exactly. We'll be dissecting these fundamental trade-offs that are always at play. The delicate balance between learning just from raw experience, often trial and error, and the immense power of foresight of being able to actually think ahead and plan.
Experience versus thinking it through.
Precisely. So we'll start by contrasting model-free versus model-based learning. This is core to reinforcement learning. We'll explore why thinking ahead can just dramatically cut down on that trial and error process.
Makes sense.
Then we'll get into how familiar actions, things we do all the time, become habits, and how this process, which seems so simple on the surface, is actually a really sophisticated computational shortcut. It's known as amortized inference.
Okay, habits as shortcuts. I like that.
Then we'll broaden the scope a bit. We'll look at active inference. This is a really big idea, a unifying brain theory that tries to explain perception and action as fundamentally attempts to minimize surprise.
Minimize surprise. Interesting.
Yeah, we'll unpack that. And finally, we'll tackle bounded rationality. This is about understanding how our limited time, our limited brain power leads us to make decisions that are good enough rather than always striving for some theoretical perfection.
And why good enough is often the most rational approach, right, given the limits.
Exactly. It's rational because of the limits.
And, while these AI examples, like the drone, they provide a really vivid context. Our main focus here is going to remain on what this all means for us, for human behavior, human cognition.
Absolutely.
By the end of this, hopefully, you'll have a much more comprehensive, nuanced grasp of how intelligence really operates under constraints. It connects fields like computer science, psychology, maybe even a bit of philosophy. Get ready for, hopefully, some real aha moments.
Definitely. It ties a lot together.
Okay, let's build this from the ground up. Let's talk about reinforcement learning, or RL. So fundamentally, RL is about an agent learning what to do.
Right, the agent is the learner, the decision maker.
And by agent, we really mean anything, right? It could be a person, an animal, or an AI. Anything that can perceive its environment, take actions.
And crucially, learn from the consequences of those actions.
Exactly. So it's learning how to map situations to actions. And the ultimate aim, it's always to maximize some kind of cumulative reward over time.
Yeah, it's not just about one single good outcome. It's about the total benefit, the sum of rewards you get over a whole sequence of actions, a sustained pattern of success.
So consistency matters.
Absolutely. To make this a bit more concrete, let's imagine a really simple scenario, like a grid world. Think of a little checkerboard.
Okay.
You have an agent, maybe represented by a little robot icon, and it starts in one square. There's another square designated as the goal.
The target.
Right. And the agent can move, say, up, down, left, to right. Now, here's the RL part. It gets a positive reward, maybe plus 10 points, only when it lands on that goal square.
Only at the very end.
Exactly. And maybe it gets a small negative reward, like -1, for every single step it takes. This represents a cost, like time or energy.
So it wants to get there, but efficiently.
Precisely. The agent's task is to figure out the best path, the sequence of moves that gets it to the goal while minimizing those step costs. It has to learn the optimal policy. This simple setup is great because it lets us really clearly compare different ways of learning.
Okay, so that sets the stage. Now, how does an agent actually learn this? This brings us to that first big distinction you mentioned, the model-free approach.
Right. So in model-free RL, the agent doesn't actually try to build an explicit internal understanding or representation of how its actions change the environment.
He doesn't build a map in its head.
Exactly. There's no internal simulation of the world's physics or its cause and effect rules. It doesn't understand why moving right from square A leads to square B.
So how does it learn then?
Well, instead of constructing that internal model of, the world's transition dynamics, how states change given actions the model-free agent learns directly, it learns which actions in specific situations tend to lead to rewards.
Based purely on past experience.
Purely on past experience. It's essentially building up, like you said earlier, a kind of lookup table in its memory. For any given square on the grid, it learns a value for moving up, down, left, right, based entirely on whether those moves eventually led to the goal in the past.
So it knows moving right from here has been good before, but not why.
Exactly. It doesn't know the underlying structure, the intermediate steps, or the reason that move was good. It just knows. This action in this state has, on average, resulted in that reward down the line. It's purely associative.
It sounds very reactive.
It is. And what's really fascinating is that this idea, this way of learning, it has incredibly deep roots in early psychology. We're talking over a century ago with Edward Thorndike and his law of effect.
Thorndike's cats.
The very same. His famous experiments putting cats in these puzzle boxes, the cats would initially just flail around, trying random things.
Thrashing about.
Right, until purely by chance they'd stumble upon the correct action, like pulling a specific string or pressing a lever that opened the door and let them get to food.
The reward.
The reward. And Thorndike observed that the successful behavior, the one that led to escape and food, got stamped in. It became much more likely to be repeated the next time the cat was in the box.
So the connection got stronger.
Exactly. And Thorndike argued the cat wasn't really understanding the mechanism of the box. It wasn't reasoning it out. It was simply learning through the direct consequences of its actions without needing any explicit foresight. That's the absolute core of model-free learning.
Wow. So the AI concept really mirrors that early psychological insight. But you mentioned limitations earlier. What's the downside of learning this way?
Well, that directness, that reliance purely on experienced outcomes is also its major weakness. Because it doesn't understand the underlying cause and effect, model-free learning needs a huge amount of data, tons and tons of repetitive practice.
Like the drone needing to crash potentially many times.
Precisely. Our delivery drone crashed because its learned policy, its lookup table of actions, didn't include any understanding of the physical consequences of hitting a tree. It only knew deliver package is good reward. There was no explicit negative feedback programmed in for the act of hitting an obstacle itself.
So unless hitting the tree directly prevented the final reward, it wouldn't learn to avoid it quickly.
Exactly. It highlights this problem called sample inefficiency. You need an enormous number of real-world interactions, which can be incredibly costly, time-consuming, or even dangerous, just to solidify a reliable policy. The drone might have had to literally crash many, many times before the association between approaching tree and bad outcome, failed delivery, became strong enough to change its behavior. And that's assuming the reward structure even allowed for that learning.
Right. So it's kind of dumb but fast in a way.
Yeah.
Once it has learned that lookup table after all that experience.
The execution is incredibly quick. It just looks up the best action for the current state. Very little computation needed at decision time.
But the learning process itself is painstakingly slow and data hungry. That really highlights the trade-off. Okay, so that's the model-free world. What's the alternative then?
The alternative is the model-based approach. And this is where things get quite different. In contrast to model-free, a model-based reinforcement learning agent does actively try to build an explicit internal model of its environment.
So it does build that mental map.
Exactly. This model is essentially its understanding of how the world works, how states lead to other states, giving certain actions. It learns the rules of the game, the transition dynamics.
How would it build this map?
Typically by observation and interaction. As it takes actions, it observes the outcomes and starts to notice patterns. Whenever I'm in square C and I move right, I consistently end up in square D. It learns these connections, building up an internal representation of the grid world's layout and rules.
So it's learning the cause and effect.
Precisely. Think of it like a human mentally visualizing different routes on a map before starting a journey. Or maybe a chess grandmaster playing out sequences of moves in their head, predicting the opponent's responses.
Simulating possibilities.
That internal simulation capability is the real hallmark of model-based reasoning. And just like model-free, this idea also has fascinating parallels in psychology, particularly with Edward Tolman's work on rats and mazes back in the mid-20th century.
Tolman's cognitive maps, right?
Yeah, exactly. His famous latent learning experiments were key. He'd let one group of rats just wander around a complex maze with no food reward, no reinforcement at all.
Just exploring.
Just exploring. Another group learned the maze the standard way with food at the end. Later, when food was introduced for the exploring group, they learned to find it incredibly quickly, much faster than rats who were only just seeing the maze for the first time.
So they must have learned something during that exploration phase, even without rewards.
Tolman argued yes. They had formed an internal cognitive map of the maze's layout, its structure, purely through exploration. They had learned the model of the environment, even without explicit reinforcement signals driving that learning.
That's a powerful idea. So what's the big advantage of having this internal model?
The biggest advantage is sample efficiency. Because the agent has this internal map, it can simulate outcomes in its mind without having to perform costly or risky actions in the real world.
It can think ahead?
It can think ahead, it can plan sequences of actions towards a goal, effectively running experiments inside its own model. This allows it to avoid countless fruitless trials in the real environment.
Can you give a real-world example?
Sure. Let's go back to your commute. Imagine you usually take the same route to work every day. That's maybe your model-free habit.
Right, autopilot.
Exactly. But one morning, you hear on the radio there's a major accident blocking your usual road. Now, a purely model-free driver, locked into their habit, might just keep going until they physically hit the roadblock. They only react after experiencing the negative outcome.
Frustrating.
Very. But a model-based reasoner. Upon hearing that new information, they can access their internal map of the city, mentally simulate alternative routes, consider traffic patterns, and immediately choose a detour before even leaving the house.
Proactive adaptation.
Precisely. It demonstrates the ability to make much fuller use of available information, integrate new data quickly, and adapt behavior with far, far fewer potentially negative real-world interactions. The planning avoids the real-world trial and error.
Okay, so model-based reasoning offers foresight, flexibility, much better sample efficiency. It sounds way more powerful. But you hinted there's a cost.
There's always a trade-off. Building, maintaining, and using that internal model isn't free. It requires significant computational resources.
More brain power, basically.
Exactly. Running those simulations, planning sequences of moves that incurs a real deliberation cost. If the environment is very large, very complex, or changes extremely rapidly, building an accurate model might be too slow, or the planning process itself could become computationally intractable. It might take too long to figure out the best move.
So model-free is dumb but fast execution, while model-based is smart but potentially slow deliberation.
That's a great way to put it. Model-free habits are quick and automatic once learned. Model-based planning offers immense flexibility and adaptability, especially to novel situations, but it comes at the cost of that deliberation time and computational effort.
So what does this all mean for us then, for humans? Are we purely one or the other, or is it more complicated?
It's definitely more complicated, and this is where it gets really interesting. What we see in humans, and actually also in the most advanced AI systems like DeepMind's AlphaGo,
I'll go playing AI.
Right, is a sophisticated dynamic mixture of both model-free and model-based strategies. We aren't locked into one mode.
We switch between them.
We switch seemingly effortlessly. We instinctively rely on those fast, efficient, model-free habits for routine, familiar situations where the stakes are low. Think about brushing your teeth or tying your shoes. You don't consciously plan each micro-movement.
Definitely not.
It's pure autopilot. But we can seamlessly shift gears into deliberate model-based planning when we encounter something unexpected, something novel, or when the consequences of a decision are really high and require careful consideration.
Like the road closure example. Or maybe deciding on a major life change.
Exactly. If that familiar routine is suddenly disrupted, or if the decision is complex and important, we engage the planning machinery.
And what triggers that switch? How does the brain decide which system to use?
That's a key research question, but uncertainty seems to play a huge role. Our brains appear to constantly, implicitly monitor how well our current strategies are working. If our cached habits, our model-free predictions are reliably leading to good outcomes, we tend to stick with them. Why fix what isn't broken, right? It saves energy.
Makes sense.
But if the situation seems genuinely new, or if the outcomes of our habits become unpredictable, more uncertain, or if our internal model becomes highly confident that it knows a better way, even if it requires effort, that's when we're more likely to engage the deliberate model-based system.
So uncertainty or a clear potential benefit pushes us towards planning.
It seems so. It really highlights the brain's incredible ability for dynamic resource allocation. It's constantly managing this trade-off between exploiting well-learned, efficient habits and exploring new possibilities through effortful planning.
Okay, let's do a quick recap here. We've unpacked this fundamental difference, right?
Yeah.
Learning by doing versus learning by thinking. Model-free is quick, reactive, almost reflexive, like building a habit through sheer repetition.
Yeah.
Think Thorndike's cats.
Right, the law of effect in action.
Whereas model-based involves building that internal mental map, that cognitive map like Tolman's rats have, which allows for foresight, planning, and much more flexibility.
Exactly. And critically, neither system operates in isolation, at least not in complex beings like us or advanced AI. We blend these approaches, dynamically switching based on how novel or uncertain a situation feels or how high the stakes are.
It's this fundamental trade-off.
Yeah.
Speed and efficiency on one side versus flexibility and foresight on the other. And this dynamic interplay really sets the stage for understanding how our brains manage the sheer complexity of everyday decision-making.
Precisely. It's the foundation upon which more complex cognitive strategies are built.
Right, which then leads to this really interesting, maybe even paradoxical question. If model-based planning, that foresight, is so powerful, so flexible, why do we rely so much on habits? Things that on the surface seem less intelligent, more rigid, it feels a bit counterintuitive.
It does, doesn't it? And digging into this paradox is where we get to a deeper level of understanding computational rationality. The key insight is that model-free habit learning isn't just some sloppy byproduct of repetition. It can actually be seen as a highly sophisticated, computationally rational strategy.
Rational? How so?
It's a way of amortizing the cost of decision-making over time. Amortizing, like spreading out a cost.
Okay, explain amortizing in this context.
So think about it in machine learning first. Amortized inference is a technique where you pre-compute or learn an approximate solution to a problem once or over time. You do the heavy lifting up front or incrementally.
So you don't have to recalculate it from scratch every single time you need it.
Exactly. You avoid that expensive, potentially slow recalculation for every new query or decision. It's like, think of a software compiler. It takes human-readable code, which is slow to interpret, and translates it once into highly efficient machine code.
So the program runs much faster later.
Right. It's amortized the cost of interpretation over all future runs.
Okay, so how does that relate to human habits?
Well, similarly, it seems humans and other animals convert slow, effortful, deliberative processes, things that initially require model-based planning, into fast, low-effort habits through repetition.
Like learning to drive stick shift.
Perfect example. Initially, driving stick requires intense concentration, right? You're consciously thinking about engine RPMs, clutch position, coordinating feet and hands. It's very model-based and mentally taxing.
Absolutely exhausting at first.
But after weeks, months, years of doing it, those actions become smooth, automatic. It becomes a cached policy, as some researchers call it, a reflex, a habit, executed with minimal conscious thought.
You don't think about it anymore, you just do it.
You just do it. Your brain has effectively pre-computed or compiled the solution into an automatic motor sequence. In reinforcement learning terms, you've gradually built up that super fast lookup table of action values, not necessarily through planning anymore, but through the repeated experience of successful execution. Instead of calculating the optimal clutch release on the fly every time, you just retrieve the learned motor program.
So the habit is the compiled code.
That's a fantastic analogy. And as cognitive RL models suggest, habits seem to arise from this kind of action selection, relying on a cached value lookup. And the big advantage, it demands significantly less cognitive effort compared to goal-directed action selection, which always requires firing up that internal model and running those mental simulations.
It's like using a cheat sheet instead of solving the problem from first principles every time.
Precisely. Your brain develops this quick muscle memory or mental shortcut for recurring situations, freeing up your conscious attention, your cognitive bandwidth for other things.
Okay, so that compiled code analogy works really well for the speed benefit. But compiled code is also usually inflexible, right? You can't easily change it once it's compiled. Does that apply to habits too?
It absolutely does. That analogy perfectly captures both the profound upside the efficiency and the significant downside. From a pure efficiency standpoint, forming habits is incredibly rational. Why spend precious mental energy solving the same problem over and over if you can just store the solution and retrieve it instantly?
It seems brainpower.
Hugely. It frees up our cognitive RAM for tackling genuinely new problems or making really critical decisions that do require careful thought.
But the inflexibility,
Yeah.
what happens when things change?
That's the major drawback. If the environment suddenly shifts, maybe the reward associated with the habit disappears or the outcome changes, maybe it even becomes negative. A purely ingrained model-free habit will often persist mindlessly.
It keeps running the old code even though the situation is different.
Exactly. It continues executing that compiled sequence, at least for a while. It takes a significant amount of new, disconfirming experience, negative feedback to potentially force an update or break the habit.
Like our drone again.
Perfectly illustrated by the drone crash. Its policy was essentially a habit optimized for reach destination. Its compiled code utterly lacked the flexibility to incorporate unexpected dynamic information like that suddenly appearing tree. It hadn't learned a general rule about avoiding obstacles, only a specific rote-reward association. That rigidity is the price of habitual efficiency.
Right. That makes a lot of sense. So when are we most likely to fall back on these efficient but potentially rigid habits? What conditions push us towards that autopilot mode?
This is where the idea of cognitive load becomes absolutely central. We humans are constantly, often unconsciously, managing this trade-off between effortful planning and automatic habits. And the balance shifts, especially when we're under pressure.
What kind of pressure?
Well, experiments consistently show that when people's cognitive resources are taxed, maybe they're trying to do two things at once, or they're under strict time pressure, or they're just mentally fatigued, maybe stressed.
Basically, when the brain is already working hard.
Exactly. Under those conditions, people tend to rely much more heavily on habitual, model-free choices, even if those choices aren't strictly the best anymore.
Why would the brain do that? It seems counterproductive if the habit is wrong.
It's the brain's incredibly clever, albeit sometimes flawed, way of saving bandwidth. When deliberate model-based thinking is simply too costly, too resource-intensive given the current demands, the brain defaults to the lower effort option. The precompiled habit, the autopilot behavior,
It conserves energy.
conserves precious cognitive energy. And this phenomenon aligns perfectly with this core idea we're building towards, that we are fundamentally resource-rational beings. We're not just optimizing for external rewards like money or food. We are implicitly, constantly optimizing for the internal cost as well, the cost of the mental effort required to get those rewards. Our brains are performing an internal cost-benefit analysis on their own thinking processes.
Wow. Okay, let's recap this section then.
Yeah.
We've seen that habits aren't just, lazy shortcuts or bad patterns. They're actually computationally efficient cached plans or compiled code. This process, called amortized inference, lets our brains save a ton of valuable processing effort by reusing solutions for problems we face repeatedly.
Right, a very rational strategy from an energy perspective.
But the big trade-off is inflexibility. Habits can persist mindlessly even when the situation changes, leading to potentially suboptimal outcomes, like our poor drone hitting the tree.
The price of automation.
And crucially, when our brains are under load, tired, stressed, multitasking, we lean even more heavily on these efficient, if sometimes rigid, automatic behaviors. It reflects our brain's deep-seated drive to conserve its limited cognitive resources.
Absolutely. It's constantly weighing effort versus reward. And this points towards an even deeper, perhaps more unified principle underlying how we perceive the world and decide how to act within it. Which brings us neatly to the concept of active inference.
Okay, so our discussion so far has mostly centered around, maximizing rewards, learning from trial and error, the interplay between habits and planning. But now we're going to shift gears a bit and look through a different, maybe even more ambitious lens.
Yeah.
This comes more from cognitive neuroscience, and it offers a potentially unifying framework that goes beyond just simple rewards. We're talking about active inference.
Indeed. Active inference is a really powerful and I think quite elegant theoretical framework. It's primarily rooted in the free energy principle, which was proposed and developed by the neuroscientist Carl Friston.
Friston, right. Heard the name. It sounds complex.
It can get mathematically deep, but the core idea is surprisingly intuitive, yet also quite profound. It posits that all intelligent agents, especially complex biological systems like brains, are fundamentally driven by a constant effort to minimize surprise.
Minimize surprise, like avoiding jump scares.
Not quite like that. Surprise here is a technical term from information theory. It basically means the mismatch, the difference between what an agent's internal model predicts it will sense and what it actually senses from the environment.
So prediction error.
Exactly. Prediction error is a great way to think about it. The brain isn't just passively soaking up information from the world, it's constantly actively generating predictions about the sensory input it expects to receive next, based on its internal model of how the world works.
It's always guessing what's coming.
Continuously. And when those predictions are violated, when reality doesn't quite line up with the internal model, that difference, that error signal is surprise. And the core idea of active inference is that the brain fundamentally works to keep the surprise low over time.
Okay, so it wants its predictions to be accurate. How does this relate to goals or rewards then? If it's not about maximizing reward, what's driving behavior?
This is a key difference. Within the active inference framework, the agent doesn't have an explicit, separate reward signal, like in standard RL. Instead, it encodes its goals, its desires, its preferred outcomes directly into its internal model as prior beliefs or preferences about the states it expects to be in.
So the goal is just a strongly held prediction. I expect to be in this desirable state.
Precisely. The agent prefers certain sensory outcomes, and it encodes these preferences as predictions. Then its fundamental drive, its entire purpose, becomes taking actions that actively work to make those predictions come true, to make the external reality conform to its internal preferred model.
So it acts to reduce the surprise that would occur if reality didn't match its desired state.
You've got it. It acts to fulfill its own expectations. As one description puts it simply, active inference is based upon the idea that sentient behavior depends upon our brain's implicit use of internal models to predict, infer, and direct action. It's this continuous dynamic loop. Predict, observe the resulting surprise, or lack thereof, and then act or update beliefs to minimize future surprise.
Okay, so the brain is this prediction engine, constantly trying to match its guesses to reality. What happens when the predictions are wrong? When surprise inevitably occurs, how does it handle that error?
This is where the elegance really shines. When the world violates its predictions, generating that surprise or prediction error, the active inference framework proposes a fundamental dual response. It's like two sides of the same adaptive coin, both aimed at reducing that error.
Two ways to deal with being wrong.
Exactly. On one hand, the brain can update its internal beliefs. It can change its internal model to better match the observed reality. This is essentially perception and learning.
The world isn't quite how I thought. Let me adjust my map.
Precisely. If you walk into a room expecting it to be empty and someone's there, the surprise signal triggers an update to your internal model of the room's current state. That's perception integrating new information.
Okay, so updating the internal model, what's the other side of the coin?
The other side is taking action. The brain can engage the motor system to actively change the external world so that it becomes more aligned with the original prediction.
My prediction was right, the world is wrong. Let me fix the world.
Kind of. Think about reaching for a cup you expect to be full. If it feels unexpectedly light, surprise, you might adjust your grip or lift more slowly. Or, if you predict a door should open when pushed, your preferred state is an open door, and it resists, you might push harder. You're acting on the world to make reality conform to your expectation or preference.
So perception changes the mind, action changes the world, both to reduce the mismatch.
Beautifully put. In this framework, perception and action aren't these separate, distinct modules. They are fundamentally unified. Both serve the single, overarching purpose of minimizing prediction error, of minimizing free energy, which is the long-term average of surprise. Active inference provides this remarkably coherent principle that closes the loop between sensing, thinking, and acting.
Can you give another concrete example?
Sure. Imagine your brain has an internal model that includes a preference for, say, a comfortable room temperature. It predicts experiencing that temperature. If you walk into a room and it's much colder than expected.
Surprise, prediction error.
Right. Active inference suggests you won't just stand there passively updating your belief about the room's temperature, though perception is happening. You're also likely to act to reduce that discrepancy. You might shiver in automatic action, or more consciously, you might look for a thermostat, put on a sweater, or even leave the room.
Actions driven by the desire to make the feeling match the expectation of comfort.
Exactly. The action isn't driven by some abstract reward for being warm. It's driven directly by the imperative to minimize the prediction error associated with feeling uncomfortably cold relative to your preferred state.
This really does sound like a grand unifying theory. It seems very ambitious. What makes it stand out so much?
It really is ambitious, and that's part of its appeal. One of its most powerful aspects is how it elegantly accounts for goal-directed behavior without needing that separate, explicit reward signal we talked about in RL. Goals just are preferred states, encoded as prior beliefs within the agent's generative model of the world.
So the drive to achieve goals comes naturally out of the drive to minimize surprise.
That's the idea. The agent acts to realize those preferred outcomes simply because doing so minimizes the free energy, minimizes the surprise associated with not being in those preferred states. It's a more integrated view.
Does it replace reinforcement learning then?
It's perhaps better to think of it as a generalization. Standard RL can actually be mathematically recovered as a special case of active inference if you frame rewards specifically as observations that confirm prior preferences, i.e. reduce surprise relative to desired states. So it potentially subsumes RL within a broader framework.
Wow. And you mentioned broad applications.
Incredibly broad. Researchers are using active inference to model a vast range of phenomena, everything from basic sensory perception like explaining optical illusions, why we tend to see what we expect to see, all the way up to the fine-grained details of motor control, how our movements are so precisely coordinated, and even into higher-level cognition like planning, decision-making, curiosity, attention. And there's growing work applying it to understand conditions like schizophrenia or anxiety, viewing them as potential disruptions in this prediction error balancing act.
Complex plans.
That's the unifying power it claims. All these complex processes are potentially explainable under the same mathematical umbrella of minimizing free energy. It's deeply brain-inspired, really blurring that line between thinking and doing. Both become forms of inference, the brain constantly trying to infer the hidden causes of its sensations and acting to test its hypotheses about the world.
So for someone listening, a simple way to think about it is the brain is always making its best guess about the world and what it wants.
Yeah, something like that. Always expect something. Always check if reality matches that expectation. And if there's a mismatch, a surprise. You've got two main options. Either change your mind, perception, learning, or change your actions, acting on the world. The goal is always to bring expectation and experience back into harmony, to minimize that prediction error over the long run.
Okay, so active inference, stemming from Carl Friston's free energy principle, it offers this profound shift. It suggests our brains aren't just reward seekers, but fundamentally surprise minimizers or prediction error minimizers.
Right, striving for self-consistency.
And it means our perception and our actions are really just two sides of the same coin, both driven by this innate desire to align our internal models or expectations with the reality we encounter.
A continuous dance between prediction and correction.
And astonishingly, this single framework might explain everything from basic motor reflexes up to complex cognition, unifying seemingly disparate brain functions under one principle. It really redefines what rationality might mean at a fundamental level, the brain's inherent drive for self-organization and predictability. Which leads us perfectly into the next big idea, the constraints on this whole process, bounded rationality. We have explored these incredible capabilities of the brain building complex models, the constant prediction engine of active inference, the efficiency of habits. But as we've hinted all along, the brain isn't infinite, is it? There's this recurring theme that keeps popping up, the very real cost of doing all this computation. Our brains, as amazing as they are, have limits.
Absolutely, and acknowledging those limits is critical. Biological brains, just like artificial computers, operate with fundamentally finite resources. Finite processing speed, finite memory, and perhaps most importantly, finite time to make decisions.
The clock is always ticking.
Always. Therefore, achieving what we might classically think of as optimal behavior, finding the absolute single best solution in the messy, dynamic real world, often isn't the point. Or rather, it's not practically achievable. True optimality, in a functional real-world sense, is about achieving the best possible outcome given the reasonable and feasible cost, considering those inherent limitations.
So it's about being effective within constraints, not theoretically perfect without them.
Precisely. And this profound insight isn't new. It goes way back to the brilliant economist and cognitive scientist Herbert Simon, who won a Nobel Prize largely for this idea. He introduced the groundbreaking concept of bounded rationality.
Right. What was his core argument?
Simon argued, very persuasively that real-world agents he focused mainly on humans and organizations and economies simply don't and can't operate as the perfectly rational, optimizing beings assumed in classical economic theory.
The idea of homo economicus, the perfectly rational actor.
Exactly. Simon said that's an unrealistic idealization. Humans don't have infinite time to gather all possible information. We don't have infinite cognitive power to evaluate every single conceivable option and calculate the one with the absolute maximum utility. It's just not how we work.
So what do we do instead?
Instead, Simon proposed that real agents satisfice. It's a wonderful word he coined. A blend of satisfy and suffice.
Satisfies, I like it.
It means we search for and choose solutions that are good enough. Options that meet a certain aspiration level, that cross a threshold of acceptability, rather than exhaustively searching for the absolute, theoretically optimal best. And we do this precisely because we are bounded, constrained by those very real finite resources, limited time, incomplete information, and our own inherent limits on computational capacity.
So satisficing is a rational response to having limits.
That was Simon's revolutionary insight. It is the rational thing to do when computation itself is costly.
Okay, so Simon laid this foundation in economics and psychology. How did this concept then get picked up and formalized in the world of AI, which often strives for optimality?
That's where Stuart Russell and his colleagues made a huge contribution. They took Simon's intuitive ideas and gave them a rigorous mathematical footing within AI, introducing the concept of bounded optimality.
Bounded optimality, how is that defined?
It provides a formal definition. An agent is considered bounded optimal if its program, meaning its internal algorithms, its entire decision-making architecture, represents the optimal solution to a very specific, constrained optimization problem. The constraints are defined by two things: the agent's own computational architecture.
Like its hardware, its processing speed, memory limit.
Exactly. Its physical or algorithmic limitations. And second, the specific task environment it's operating within.
So optimal given its limits and the problem it faces.
Precisely. In simpler terms, a bounded optimal agent isn't necessarily making the absolute best decision that some hypothetical, omniscient, infinitely powerful computer could make. No, it's making the best possible decision that its specific hardware and its allocated time budget actually allow it to compute.
Even if that decision isn't the theoretical ideal.
Even if it isn't, it's the optimal decision for that agent, given its real-world constraints. Russell and others proposed this as a much more realistic, much more achievable gold standard for designing intelligent agents, compared to the often impossible ideal of perfect rationality. It helps bridge that gap between abstract theory and practical implementation.
So this really implies a fundamental shift in how we even define rationality, doesn't it? It's not just about the final outcome anymore. The process, the cost of thinking, becomes part of the equation.
Exactly. And that leads us directly to the term computational rationality. This represents that paradigm shift. It means redefining what we consider a rational action to explicitly, formally include the cost of computation as an integral part of the problem the agent is trying to solve.
So rationality includes being efficient with your own thinking.
Yes. The idea is that a truly rational agent, in this computational sense, should be trying to maximize a more sophisticated kind of utility function. This function wouldn't just track external rewards, like the drone's package delivery. It would also incorporate a penalty term reflecting the internal costs incurred during deliberation.
Costs like time spent thinking, memory used, maybe even energy consumed.
All of those. So the best algorithm, the most rational strategy from this perspective, isn't necessarily the one that could eventually output the absolute highest external reward if you let it run forever. No, the best algorithm is the one that achieves the best possible trade-off between that external reward and its own internal computational cost, given the agent's specific limitations. It's about optimizing the whole system outcome and process.
And the amazing thing is, it seems like we humans are naturally pretty good at striking this balance, almost intuitively. It feels like our cognition already operates on these resource-rational principles.
That's exactly what a lot of exciting recent research in cognitive science and neuroscience is strongly suggesting. It seems our human decision-making strategies, even the ones that seem quirky or biased at first glance, often reflect a near-optimal balance between achieving accuracy, or getting rewards, and minimizing the cognitive effort involved.
We're not just trying to be right. We're trying to be right efficiently.
Couldn't have said it better myself. There was a really landmark study in 2020 by Samuel Gershman, who's a leader in this area. His work provided a formal mathematical model of decision-making, not just as maximizing reward, but as simultaneously minimizing something called policy complexity.
Policy complexity, what does that mean?
Think of policy as the agent's strategy, its set of rules for how to act. Policy complexity, then, is a measure, often using tools from information theory, of how complicated that strategy actually is. How many rules does it involve? How much information does it need to store or process to execute? A simpler policy is inherently less complex.
Okay, so simpler strategies are less complex. What did Gershman's model show?
The mathematical analysis produced a really striking result. It showed that if you set up an optimization problem where the goal is to maximize a combination of get external reward and keep the policy simple, i.e. minimize complexity, the optimal solution naturally exhibits a bias towards repeating previous actions.
Wait, optimizing for simplicity leads to habit.
Yeah.
Sticking with what you did before.
Exactly. It predicts a natural tendency towards habitual persistence or perseveration. Even if there might be a slightly better new option available, the brain, optimizing this combined objective, will tend to stick with the current, simpler, already running policy unless the new option offers a significantly better reward enough to overcome the inherent cost or complexity of switching strategies.
Wow. And did this match how people actually behave?
Amazingly well. The human data from decision-making experiments closely matched the predictions of this reward complexity trade-off model.
Yeah.
People seemed to achieve near optimal balances, and they exhibited exactly the kind of slight bias towards repeating actions that the theory forecast.
That's huge.
Yeah.
It means some of our seemingly irrational habits or biases
Might actually be perfectly rational adaptations to our cognitive constraints. It's not necessarily that we're lazy or flawed when we stick to a habit. It could be that our brain is running a very sophisticated optimization calculation, balancing external success with the internal cost of mental effort and strategy complexity.
So the brain has its own internal performance metric it's optimizing.
It seems very likely. This also connects to something called the scaling laws of deliberation. Think about effort versus reward.
Okay.
The first bit of complexity you add to your strategy, the first bit of extra thinking you do, often yields a pretty big jump in reward or accuracy. You get a lot of bang for your buck initially.
Diminishing returns.
Exactly. As you add more and more complexity, as you spend more and more mental effort refining your strategy, the extra gain in reward gets smaller and smaller. You hit diminishing returns. An optimal agent, from this computational rationality viewpoint, will stop deliberating, stop adding complexity at the precise point where that extra ounce of brain power just isn't worth the tiny marginal improvement in the outcome.
We all feel this intuitively, right? At some point, overthinking a decision just isn't worth the time and stress. A good enough decision now is better than a theoretically perfect one later.
Absolutely. We experience this trade-off constantly, and this perspective provides a beautiful explanation for the interplay between habit, model-free, and deliberation, model-based, that we discussed earlier. Well, planning every single action from scratch using your full model-based system is computationally expensive. So in stable, predictable situations, it becomes computationally rational to cache that plan, to compile it into a low-effort habit, amortized inference. You reuse the solution. Even if that habit isn't always perfectly optimal in every single instance, it saves a huge amount of time and energy on each use, making it optimal overall when you factor in the cognitive cost.
So apparent suboptimality in one dimension, maybe sticking with the slightly worse option, can actually be optimal when you consider the hidden cost of thinking or switching.
That's the core idea. Behavior that looks suboptimal if you only look at the external reward might actually be globally optimal once you factor in the internal cost, the cost of computation, the cost of switching strategies, the cost of gathering more information.
So this really reframes things. It means our biases, our heuristics, our habits, they aren't necessarily flaws in the system. They could be the features that make the system work efficiently, given its limits.
Exactly. That's the powerful conclusion emerging from this computational rationality perspective. It emphasizes that we humans adapt not just to the demands of the external world, but also, crucially, to the inherent constraints of our own minds. Our cognitive architecture matters.
Our brain is essentially solving this incredibly complex, constrained optimization problem all the time.
In effect, yes. It's implicitly asking, what is the best possible strategy I can realistically run on this limited neural hardware with this amount of time to achieve my goals in this specific environment?
And heuristics and biases are the brain's clever answers to that question.
They can be seen as exactly that. Not necessarily bugs, but highly adaptive features, cost-saving shortcuts that are remarkably effective, near optimal under the typical conditions we face in the real world.
Can you make that concrete again? Maybe the restaurant example.
Sure. Choosing a restaurant for an important dinner, the perfectly rational, unbounded agent would need to gather all data, read every single review for every single restaurant in the city, cross-reference menus with dietary needs, optimize for travel time, ambiance scores, price points. It could take days.
Completely impractical. Nobody does that.
Right. The bounded rational, computationally rational solution is what we actually do. Maybe ask a couple of trusted friends for recommendations, quickly check online reviews for the top 2 or 3 suggestions, and pick one that seems good enough, that meets our basic criteria. Satisficing. You save potentially hours or even days of effort and analysis. The cost. A small theoretical risk that you might have missed out on a restaurant that was marginally better according to some idealized metric. But the saved effort usually far outweighs that tiny potential loss. We make these kinds of efficient trade-offs constantly, and computational rationality suggests we often do so in a way that's optimally adapted to our mental resources.
And the driving home example fits here too.
Perfectly. Driving home on autopilot relies on that cached, model-free habit. Why? Because 99% of the time, that route is perfectly adequate, and the mental effort required to actively replan the route from scratch every single day, considering microfluctuations in traffic, just isn't worth the potentially minimal time savings.
The cost of thinking outweighs the benefit.
Usually, yes. It only becomes rational to invoke the effortful, model-based planning system when a significant change occurs, something that generates a large surprise or prediction error, like that unexpected road closure. And crucially, our brains seem equipped with precisely these kinds of mechanisms: sensitivity to uncertainty, surprise signals that trigger the switch from efficient habit to effortful planning when it's most likely to be worth the cost.
Wow. Okay, we have covered a tremendous amount of ground today, from that basic difference between learning by doing versus learning by planning.
Model-free versus model-based.
To understanding how our habits are actually these incredibly clever efficiency hacks, this amortized inference.
Compiled code for the brain.
Then diving into active inference, this idea of the brain fundamentally trying to minimize surprise, unifying perception and action.
The predictive brain.
And finally, landing on bounded and computational rationality. Realizing that our cognitive limits aren't just constraints, they actively shape rational behavior, making good enough often the smartest way to go. It's a really powerful testament to the sheer elegance of how intelligence operates under limits.
It truly is. It paints a much richer, more nuanced picture of decision-making. Maybe it would be helpful to quickly run through those core concepts again, almost like a set of mental flashcards for listeners.
Great idea. To fire away.
Okay, first, reinforcement learning, RL itself, that's the basic framework. An agent learns to map situations to actions, aiming to maximize some cumulative reward over time.
Got it.
Then, model-free RL. This is learning directly from experience, from rewards and punishments. Think trial and error, Thorndike's law of effect. No internal world model is built. It's reactive, often data-intensive to learn, but execution is dumb but fast.
Okay. Model-free, direct experience. Fast, but rigid.
Next, model-based RL. Here, the agent does learn an internal model of how the environment works, its dynamics. This allows for simulation, planning ahead, like Tolman's cognitive maps. It's much more sample efficient, learns faster from less data, but the planning itself is computationally heavier.
Model-based, internal map, flexible, but costly.
Then we had amortized inference, which is how habits can be seen as cached plans. Deliberative, model-based processes through repetition become fast, low-effort, model-free habits. They act like pre-computed solutions or compiled code to save mental effort.
Habits is efficient compiled code.
Right. After that, active inference. This is the unifying brain theory rooted in Friston's free energy principle. The core idea is that agents act to minimize surprise or prediction errors. They do this either by updating their beliefs to match reality, that's perception, or by taking action to make reality match their preferred beliefs or predictions, that's action. Goals are essentially preferred states the agent expects to be in.
Minimize surprise by changing mind or changing world.
Exactly. Then, bounded rationality, Herbert Simon's crucial insight. Real agents don't optimize perfectly because they have finite cognitive resources. Time, memory, processing power. Instead, they find solutions that are good enough.
Satisficing due to limits.
Which led to bounded optimality, Stuart Russell's formalization in AI. An agent is bounded optimal if its program is the best possible solution it can find, given the constraints of its own computational architecture and the specific task environment. Optimal for its resources.
Best possible performance under constraints.
And finally, computational rationality. This brings it all together. It redefines rationality to explicitly include the cost of computation. The brain, from this perspective, is optimizing a utility function that balances external rewards against the internal costs of cognitive effort. Think Gershman's policy complexity research. This explains why seemingly irrational habits or heuristics can actually be highly rational, resource-efficient adaptations.
Rationality includes thinking efficiently.
And wrapping it all up for humans. Human decision-making seems to be this dynamic, sophisticated interplay between model-free habits and model-based deliberation. The switch is often triggered by uncertainty or surprise, and the whole process is fundamentally constrained by our cognitive resources, leading to behavior that is ultimately radical enough for our complex world.
That's a fantastic summary. A really coherent picture emerges. Now, we've unpacked all these powerful ideas. How can you, listening right now, actually apply them? How can you use this framework to understand your own thinking and behavior better?
That's a great question. One practical thing you could try is what we might call a policy audit. It's a way to consciously examine the interplay of model-based and model-free processes in your own daily life.
Okay, a policy audit. How does it work?
First, just identify one specific area, one domain in your life where you feel like you operate largely on habit. It could be your morning routine, maybe certain snacking habits, how often you check your phone, maybe even the route you always take driving somewhere familiar. Pick one.
Got one.
Next, try to reflect. What was the original reward or the positive outcome that this habit was initially based on? Why did it form in the first place? Maybe that particular snack used to genuinely satisfy hunger or provide a needed energy boost. Maybe checking that app used to reliably bring you joy or useful information. There was usually a reason it got established.
Right. Habits form because they work, initially at least.
Exactly. Now here's the crucial step, the audit part. Imagine, or even better, actively observe whether that original reward or value is still there. Has it changed? Has it disappeared? Maybe that snack now just makes you feel sluggish afterward. Maybe that app has become mostly a time sink, generating anxiety rather than joy. Evaluate the current outcome.
So check if the reward is still valid.
Precisely. And the key diagnostic question is, does your behavior, the habit itself, stubbornly persist even when its original value seems to be gone, or significantly reduced, or maybe even negative now?
Do I keep doing it anyway?
Yeah. If you find yourself continuing the behavior largely out of sheer routine, almost automatically, even when you consciously know it's no longer serving your current goals or well-being, then you've likely identified a strong, model-free habit in action. It's become detached from its original value and is running on autopilot, resistant to change without explicit reevaluation.
That's really insightful. It's like finding code that's still running even though it's obsolete.
It's very much like that. This whole exercise is inspired by what psychologists call outcome devaluation experiments, which are designed to distinguish habitual versus goal-directed control. So the call to action is, once you identify such a habit, try consciously engaging your model-based system. Step back, reevaluate the behavior explicitly in light of your current goals and values. Ask yourself, would a different action actually serve me better right now? It's about bringing conscious awareness back to potentially outdated routines.
A manual override for the autopilot.
I like that.
Now, for those listeners who maybe have more of a technical bent, interest in the science, math, maybe computation side of things, you mentioned a coding challenge.
Yes. For those who enjoy tinkering, actually implementing some of these ideas can really solidify the intuition. A classic exercise is to build a simple grid world environment. Describe it verbally. Imagine a grid, maybe 5 by 5 or 10 by 10 squares. The agent starts at one square and there's a goal square somewhere else it needs to reach.
A little robot again.
Right. Now try implementing and comparing two different agents operating in this grid world.
Okay.
Agent 1 uses a purely model-free RL algorithm. Something like basic Q-learning is a good starting point. Give it a very sparse reward, say. It only gets a positive reward when it actually lands on the goal square, and maybe small negative rewards for bumping into walls or just for each step taken.
So it has to stumble upon the goal by chance initially.
Exactly. Agent 2, on the other hand, uses a model-based strategy. This agent would first explore the grid a bit to learn the layout, learn the model of which squares connect to which. Then it would use that internal map to plan an optimal path to the goal, maybe using an algorithm like value iteration or even a simple search algorithm on its learned model.
Okay, Model-free versus model-based in code. What should you look for?
Start both agents at various random locations and track how many steps or how many episodes, attempts to reach the goal, each one needs on average to find the goal. You will almost certainly observe that sample complexity gap we talked about.
The model-free one will struggle at first.
Dramatically. The model-free agent will likely wander around seemingly randomly for a long time, especially in larger grids, until it accidentally finds the reward and starts propagating that value back. The model-based agent, however, once it has explored enough to build a decent map of the grid, can often compute or simulate the optimal path very quickly and follow it directly, requiring far fewer real-world steps to succeed consistently. It vividly demonstrates the power of planning.
So you see the efficiency difference firsthand.
Absolutely. And then, for extra credit, you can start tinkering. What happens if you add a cost for the model-based agent's planning steps? Maybe each step of its internal simulation takes time, adding a penalty, or make the grid dynamic, maybe walls appear and disappear randomly.
Introduce uncertainty and cost.
Right. Suddenly, the agent that meticulously plans everything perfectly might start to struggle if the world changes too fast, or if thinking itself is too expensive. In some scenarios, a more reactive, perhaps slightly suboptimal but faster habit-based agent might actually outperform the complex planner. You get to witness bounded optimality emerge directly from the interaction of the agent's algorithm, its computational costs, and the environment's dynamics.
That sounds like a fantastic way to build intuition.
It really is. Plus, it can be quite fun to watch your little autonomous agents learn and adapt or fail to adapt. Just try to make sure they don't crash into any virtual trees in your simulation.
Right. We want to avoid repeating our initial cautionary tale. Okay, bringing this all together then. Ultimately, whether we're talking about our hypothetical delivery drone or our own very real, incredibly complex human brains, we're all fundamentally trying to solve the same kind of core problem, aren't we?
It seems so.
How do we achieve our goals, whatever they may be, effectively and efficiently, navigating a world that's full of uncertainty, where we always have limited knowledge, and crucially, where we always operate under the constraints of limited time and limited computational resources?
Beautifully summarized. And the concepts we've explored today each offer a crucial piece of the puzzle for understanding how intelligence grapples with that fundamental challenge.
Right.
Reinforcement learning, particularly the model-free model-based distinction, gave us a powerful language to talk about learning from experience, trial and error, and the formation of habits versus deliberate planning.
The basic building blocks.
Exactly. Then active inference came along and painted this richer, more unified picture of a predictive, self-correcting organism constantly striving to align its internal model with the world, minimizing surprise through both perception and action.
The brain as a proactive prediction machine.
And finally, the crucial insights from bounded rationality, bounded optimality, and computational rationality served as this vital reality check. They reminded us that cognitive resources, attention, time, processing power, are incredibly precious and finite. So truly smart agents, whether they're biological or artificial, aren't the ones that are theoretically perfect. They're the ones that make the absolute most of the limited resources they actually have available. They optimize for practical efficacy within constraints.
Optimizing for the real world, not an idealized one.
Precisely.
So, by truly understanding and internalizing these principles, we don't just gain valuable insights for, say, creating better, more robust AI systems in the future. That's important, of course.
Very much so.
But perhaps even more profoundly, we gain a deeper, more nuanced, maybe even more compassionate understanding of ourselves, of why we humans do the quirky, the efficient, the sometimes brilliant, sometimes frustrating, the wonderfully complex things we do every single day.
Yeah, it reframes a lot of our own behavior.
Our actions and decisions are often deeply rational, even when they don't seem so on the surface. Sometimes they seem irrational, but usually when you really account for all the hidden costs, the cognitive constraints, the need for efficiency, maybe they're just rational enough, perfectly optimized in their own way for the constraints of these brilliant yet fundamentally limited minds that we all possess.
A rationality that respects reality, both external and internal.
Exactly. So the final thought we want to leave you with is this. Continue to observe your own habits, your own decision-making processes, maybe through this new lens of computational rationality. The deep dive into your own mind, understanding how you navigate these trade-offs. That exploration has only just begun.